Hi, I'm Hannah. My project is titled The Application of Additive Manufacturing for the Production of Patient-Specific Radiotherapy Masks and Molds. Immobilization masks are used to ensure radiotherapy treatment is accurate and to make sure the highest dose possible is given to the cancer whilst minimizing the damage to surrounding healthy tissue and organs. The masks are used to restrict patient movement to within 2 mm in any direction. Traditionally, to produce a mask, a pre-cut thermoplastic sheet is heated in hot water before being placed onto the patient's face and then molded to fit. This is then left to cool on the patient for 15 minutes before being removed. Due to the contact methods used, this process can be distressing and intolerable for anyone to undergo, even more so for those who suffer with claustrophobia and anxiety. The main aim of my project was to design, build and test a bespoke radiotherapy head-only mask using non-contact methods for the design and manufacture. An additional aim was to reduce claustrophobia and anxiety experienced during the mask production process and radiotherapy treatment. For the design, patient data was collected by 3D scanning using a handheld scanner. 4 different scans were taken, and these were then processed, including removing frames of large errors to produce a single mesh, which was then exported as an STL file. The mesh was imported into Autodesk NetFab, where it was simplified by removing errors not necessary for the design and converted from a mesh into a Brett model suitable for computer-aided design or CAD. The main CAD work was conducted in SolidWorks, where the Brett model acted as a basis from which the mask design was produced. The interface of how the mask fixes to the treatment table during radiotherapy was created, along with a cutout around the facial features to help reduce anxiety experienced during treatment. Although subtractive and formative manufacturing methods were considered, additive manufacturing, or AM, was concluded to be the most appropriate, as low volumes of these custom-made masks are required, and it was the most suitable for use with 3D scanning and CAD. The material for each mask can also be kept to a minimum. From the 7 AM technologies, binder jetting, material extrusion, and powder bed fusion were the most promising, as they had previously been used in medical facilities. Fused deposition modelling was ultimately selected as it has sufficient accuracy, build bed size, and material layer thickness, and has the lowest equipment and material costs. Polycarbonate was chosen for the mask as it is safe for contact with human skin, has good mechanical properties, and copes well when subject to radiation. Cura was the software used to generate the support structures prior to manufacture. The mask was orientated on the build bed face downwards to minimise the amount of support material required, and so that the support did not interfere with where the individual's face is placed. The prototype was created from ABS on an Ultimaker 2, used PLA as the support material, and took 4 days 9 hours to manufacture. From the testing, results found that the mask fit well, was comfortable, and patient movement was restricted, but to a slightly greater degree than the allowed 2 mm. The time a patient is required for an appointment is similar to the current process, however mask production is considerably longer, but it can be left overnight to print. A prototype immobilization mask was successfully created which restricted patient movement without the individual experiencing claustrophobia or anxiety. Mask production is longer and has a greater total cost than the current process, however this is expected to reduce over time with advancements in technology.